This is a Unit 4 practice exam for Math 1050. So we have a system of equations here. One's linear, this one is not linear. So we're going to solve this one using elimination. You can see we have like terms on x variables. We do not have like terms here on y, but we do have like terms with x. So if I multiply this bottom equation by -2, then you can see we have opposite coefficients of x. So when we try the elimination method now, the x variables eliminate. Notice that y is not like terms y squared and 2y, so when you add those together, they need to be added together as y squared plus 2y equals 0. Now we have a quadratic equation. If we factor out a y, now we can solve for y equals 0 and y equals -2. Now remember, when we're solving a system of equations, we're looking for the point or points on the graph where these two graphs intersect. So we have the y values, we need the x values. And since we have two y values, we need to solve for two x values. So when y is equal to 0, I'm going to use this bottom equation here because it's linear to solve for x. So when y equals 0, we have 3x minus 0. Instead of subtract y, I'm going to subtract 0 because y equals 0. And that's equal to 5. So x equals 5/3. When y equals -2, I'm going to use the same equation. 3x subtract y, so that's going to be subtract -2. So x equals 1. So the other solution is 1, comma, -2. And we have three equations and three variables. So what we're going to do is choose two of the equations and eliminate one of the variables. So I notice here we have 2x and -2x. So if I take the top equation and the bottom equation, and eliminate the x variable, that leaves y minus 3z equals -1. Now since there's two variables there, we're going to have to repeat this step with two of the other equations. So if I take, for example, the top two equations here, and multiply that equation there by -2, then what we'd end up with is, again, we can eliminate x, and it's important. In step 1 here and step 2, you have to eliminate the same variable. So then we end up with y minus 3z equals -1. So step 3 of this process is you take the result from step 1, you take the result from step 2, and you form a new system of equations. You can see here already, though, that the result from step 1 and the result from step 2 are identical equations. Usually it's not, which means you could solve for one of the other variables. In this case, since they're identical, if we try to do elimination method, for example, what we'd end up with is the variables cancel, constants cancel, so we have 0 is equal to 0, which is an indication of infinitely many solutions. So what we talked about in class, if there's 3 variables, meaning in this case x, y, and z, the convention in most college algebra textbooks is to let z equal t. T is a parameter. The parameter t can be any real number. So if we let z equal t, now we can go back up to this step, step 3, and take one of the equations to solve for y in this case, because we know the value of z. So we can solve for y. So then y minus 3, instead of 3z, I'm going to call that 3t. And then if you add the 3t to the other side, we get y equals 3t minus 1. Now we can use one of the original equations that have the 3 variables. I'm going to use this middle one. So x minus y plus z equals 2. That becomes x minus, I'm going to substitute y as 3t minus 1. And whenever you make a substitution, remember, especially if the substitution involves several terms, you do that substitution in a parenthesis, and then plus z becomes plus t. That equals 2. Now I'm going to get rid of the parenthesis by distributing this negative sign. And now we're solving, I'm going to solve for x, so I need to get all of these terms on the other side of the equal sign. Negative 2t just came from combining the like terms, negative 3t plus t. So I'm going to add the 2t to the other side and subtract the 1. So x equals 2t plus 1. So now my solution x comma y comma z becomes, for x we have 2t plus 1. For y we have 3t minus 1. And for z we had t. Question 3, we're going to solve, again, a system of equations involving 3 variables. But this time we're not going to use elimination method. We're going to use what we learned in section 6.3 called elementary row operations using an augmented matrix. So the first step here would be to create the augmented matrix. And remember the process is this needs to be a 1, then we want a 0 here and a 0 here. And then once that's complete, then we want a 1 here and then a 0 here. So we already have a 1 in the top left corner, so I need to get this to be a 0 and get that to be a 0. So I'm going to multiply row 1 by negative 2. Then we're going to add that to row 2 to create a new row 2. So this means everything in row 1 is going to be multiplied by negative 2. So this makes negative 2 plus 2, which is 0. Negative 2 times here makes negative 4, plus negative 1 is negative 5. Negative 2 times negative 1 is positive 2, plus 3 is 5, and then negative 2 times 6 is negative 12, plus negative 13 is negative 25. Now I also want to have a 0 right here, so if I could make this negative 3 plus that 3 would make it 0. So now I'm going to do a new row operation, negative 3 times row 1. Now I'm going to add that to row 3 to create a new row 3. So now row 1 is going to be multiplied by negative 3. Every entry in row 1 will be multiplied by negative 3, and then you add it to row 3. So 1 times negative 3 plus 3 is 0. 2 times negative 3 is negative 6, plus negative 2, negative 8. Negative 3 times negative 1 is 3. 3 plus 3 is 6. And then 6 times negative 3 is negative 18. Negative 18 plus negative 16 is negative 34. Now I want to get a 1 right here. So if I multiply row 2 by negative 1/5, that's going to make a new row 2. So I'm going to write that over here to save some space. So that's going to be 0 times negative 1/5 is 0. Negative 1/5 times negative 5 is positive 1. 5 times negative 1/5 is negative 1. And negative 25 multiplied by negative 1/5 is positive 5. Now the last thing, well, towards the end, we want to get this to be a 0. So if I multiply this row by 8, that's going to put an 8 right here. 8 plus negative 8 is 0. So I'm going to do row 2 times 8. So 8 times row 2. I'm going to add that to row 3 to make a new row 3. So the entire row needs to be multiplied by 8. Starting here, 0 times 8 is 0. 0 plus 0 is 0. 1 times 8 is 8, plus negative 8 is 0. Negative 1 times 8 is negative 8, plus 6 is negative 2. And 5 times 8 is 40. 40 plus negative 34 is 6. So now we can take this bottom row and make an equation. Negative 2z equals 6, therefore z equals negative 3. Then we can take this middle row and create an equation y minus z equals 5, and we can replace z with y minus negative 3 equals 5, so that's y plus 3. If you subtract 3, you get y equals 2. And now that top row is the equation x plus 2y minus z equals 6, which we can turn into x plus 2 times y minus z equals 6. So this is 4 plus 3, that's 7. X plus 7 equals 6, which means x equals negative 1. So the solution to our system of equations here is x equals negative 1, y equals 2, and z equals negative 3. Now when you're trying to multiply matrices together, you need to check the dimensions. For part A, for example, matrix A is a 3 by 3, and matrix B is a 2 by 3. Because these two numbers here don't match, part A is not possible. Now for part B, we're going to do matrix B times matrix A. So matrix B well, I guess we should check first. Matrix B is a 2 by 3 and matrix A is a 3 by 3. So the inside numbers there, they match, so the multiplication is possible. And the multiplication is going to result in a 2 by 3 matrix, which I'm going to write there. So this entry here is going to be a combination of this row and that column. So 1 times 0 is 0, plus 0 times 2, that's 0, plus 5, so 0 plus 0 plus 5. This entry is a combination of that column with that row, so 0 times 1 is 0, 2 times 3 is 6, 1 times 0 is 0, so 0 plus 6 plus 0 is 6. This entry is a combination of that column and this row, so 0 times negative 1 is 0, 2 times 1 is 2, 1 times negative 2 is negative 2, so 0 plus 2 plus negative 2 is 0. Now, this entry is a combination of that row to that column, so 3 times 1 is 3, negative 2 times 0 is 2, or 0 rather, and 4 times 5 is 20, so we have 3 plus 0 plus 20, so 23. This entry is this column with this row, so 3 times 1 is 3, negative 2 times 3 is negative 6, and 4 times 0 is 0, so 3 plus negative 6 plus 0 is negative 3, and finally we have this entry combining this row to that column. So that makes negative 3, that makes negative 2, that makes negative 8, so negative 3 plus negative 2 is negative 5, negative 5 plus negative 8 is negative 13. So this matrix right here is the product B times A. Now for part C, we're going to do 2 times matrix B. Well, let's check first. When we're adding or subtracting matrices, even if they're multiplied by a constant value there, we have to have equal dimensions of both matrices. So B is a 2 by 3, C is a 2 by 3, so we can subtract them. So 2 times B minus 3 times C so this is called scalar multiplication. We're just going to multiply every entry in B by 2. And then multiply all the entries in matrix C by 3. And then subtract. So 0 minus negative 9 is 9. 4 subtract 6 is negative 2. 2 subtract 12 is negative 10. 6 subtract negative 3 is 9. Negative 4 subtract 0 is negative 4. And 8 subtract 21 is negative 13. Question 5, we're going to use an inverse matrix to solve a system of equations. So the first step, if you recall from section 6.5, was to create the matrix equation. So we have the coefficient matrix, a matrix containing the variables, and then a matrix containing the constant 10 and 30. So we're solving for x and y. It's being multiplied by this matrix, so we need to cancel this matrix so that x and y can be isolated. So what we need to do is multiply by the inverse matrix here and that same inverse matrix here. So we got to find the inverse of matrix with this matrix. So if I'm going to call this here matrix A, then the inverse of A is 1 divided by A times D, so that's negative 8, minus B times C, so that's negative 9. And then remember A and D change places. And B and C, they don't change places, they switch signs. So that becomes a positive 3, that becomes a negative 3. So here in the denominator, negative 8 plus 9 is 1. So there's the inverse. So what we do now is we take this inverse, we multiply it here. So if I multiply the inverse of a matrix to itself, those cancel out. So the next step here is to take this inverse and multiply it on the left side of this matrix. So I'm going to take this inverse and multiply it by this matrix here. And find the product right there. So this entry is a combination of that row to that column, so that makes negative 20. This makes 90, so 90 plus negative 20 is 70. Now here we get negative 30 combined with 120, so that's 90. So this matrix 70 and 90 is equal to that matrix, which means the solution is 70 for x and 90 for y. Now part B is the same process as part A, but when you have 3 equations and 3 variables, you have to find the inverse of a 3 by 3 matrix, which is very lengthy and rather difficult, to be honest. And so for a problem like this, the inverse matrix will be included in the problem. So we're going to use this inverse matrix. So we still have our matrix equation. We have a matrix containing the variables, and then a matrix containing the constant values after the equal sign. So this matrix is multiplying x, y, and z. So we need to solve for x, y, and z, which means this matrix needs to be isolated. It's being multiplied by this matrix. The only way to cancel a matrix is to multiply it by its inverse. This is the inverse of this matrix. If this weren't given, we would have to find the inverse. And like I said, the inverse of a 3 by 3, to find that is a very lengthy process. So this times this means that this matrix will disappear. We also have to multiply this inverse on the left side over here. And that's what we need to show in this problem, is this matrix multiplied by this matrix, which is going to give us the values of x, y, and z. Okay, so this entry is a combination of that row and that column. So this makes -5, that's -6, and that's +5. So -5 plus -6 is -11, plus 5 is -6. Now here we're going to combine this row to that column. So 2 times 1 is 2, 1 times 3 is 3, and -2 times 1 is -2. So we have 2 plus 3, which is 5. 5 plus -2 is 3. Finally, we have this row to that column, so that makes -4, makes -9, that makes +5. So -4 and -9 make -13. -13 plus 5 is -8. So what we have here is this -6, 3, and -8 matrix is equal to our XYZ matrix, which means the solution is x equals -6, y equals 3, and z equals -8. All right, in section 6.6, we learned about determinants of a matrix and Cramer's rule. Cramer's rule uses determinants to solve a system of equations. So when you have two equations and two variables, we need three determinants. We need determinant D, which is the determinant of the coefficients. So that's 3 times 4, which is 12, minus 5 times -2, which is -10, which is 22. The next determinant, D sub x, the subscript x means the values in this x column are going to be replaced with those constant values. So instead of this 3 and 5 in the x column, we're going to have -1 and -31. And then the values in the y column stay the same. So this determinant is -1 times 4, which is -4, minus -31 times -2, which is 62. So -4 minus 62 is -66. And then the final one is d sub y. So now the subscript y means that in the y column, we're going to replace these values with these values. So -1 and -31 go in the y column. The x column stays the same as it originally was, 3 and 5. So now this determinant is 3 times -31, which is -93, minus 5 times -1, which is -5. And here we get -88. So those are the determinants. Now Cramer's rule now uses these determinants to say the value of x is the determinant d sub x divided by d. So that's -66 divided by 22, which is -3. And then y is equal to determinant dy divided by d, which is -88 divided by 22, which is -4. So our solution here is x equals -3 and y equals -4. Part B, we are going to use Cramer's rule again. If you have three variables and three equations, you need four determinants. However, this one says we only need to solve for x. So since x is equal to d sub x divided by d, then we only need those two determinants. So first we need d determinant, which is just the determinant of all the coefficients. Now in class, there were two different ways presented to find the determinant of a 3 by 3 matrix. You can use either way. I'm going to use this method where these first two columns are copied to the right side over here. We have 3, 4, 1, and 2, -1, -3. Now, these three values multiply together, these three right here. So that product is 12. The product of these three numbers is 2. And the product of these three numbers, -8 times -3 is 24. Now, I'm going to go this direction. The product of these three numbers is 2. The product of these three numbers is -9. And the product of these three numbers is -32. So the way this works now is these three numbers add, these three numbers subtract. So it's 12 plus 2 plus 24. Then we subtract the ones in blue, so that's -2 minus -9 and minus -32. So that determinant is 77. So now for this determinant, we're going to take the values here, 10, 5, and -1, and that's going to replace the x column. All others stay the same. And then I'm going to use the same method here, so I'm going to copy these two columns over here. And then in that diagonal, 10 times -1 times -4 is 40. In that diagonal, we get -2, and in this one, we get -10 times -3, which is +30. In this diagonal, we get -2. In that one, we get -30. In this one, we get -40. And we have 40 plus -2 plus 30 minus -2 minus -30 minus -40. So 40 plus -2 is 38. 38 plus 30 is 68. Plus 2 plus 30 plus 40, so that's 70 plus 30, it's 100, that's 140. So then, coming back up here, x is equal to the determinant d sub x, so that's 140, divided by determinant d, which is 77. So that means x is equal to 140 divided by 77, which is 1.81. Repeating. Question 7 is from section 6.7, finding the partial fraction decomposition. There were a few different instances of partial fraction decomposition depending on the factors of the denominator, whether they were repeated or whether they were linear. These are both linear, non-repeating. So since there's only two factors in the denominator, we're going to have two partial fractions. And then if this whole equation was multiplied by the common denominator, x minus 3x plus 5, then we'd have 9x minus 11 equals a times x plus 5 plus b times x minus 3. So now the process that was shown in class involves choosing convenient values for x, because if we only have one equation but we have to solve for two variables, we have to eliminate variables. So if x was negative 5, for example, negative 5 plus 5 is 0, so that eliminates a. So since we have two variables, we're going to have to do this twice. For the first one, I'm going to let x equal negative 5. So here this makes negative 45 minus 11, that's negative 56. Here a is eliminated because this makes 0. Negative 5 minus 3 is negative 8 times b is negative 8b, so then b is equal to 7. So we already solved for b, now we need to solve for a, which means I have to eliminate b. So if x was 3, then we have 27 minus 11, that's 16. 3 plus 5 is 8 times a is 8a. And then b is eliminated because 3 subtract 3 is 0. So this means here a is equal to 2. So now we have the values for a and b. So 2 divided by x minus 3 plus 7 divided by x plus 5.
Okay, for question 8, I wanted to walk you through what I've done here. So the first step in any application problem is to define your variables for the question. The question here is how many of each ticket were sold. And so how many tickets were there is the question, how many of each ticket? Well, there's three different types of tickets, child ticket, adult ticket, and premium. So I've just defined X is the number of child tickets sold, Y is adult tickets, and Z is the number of premium tickets sold. So that's the first step, identify and define your variables. Now the second step here was to use the given information to make equations with which you can solve the variables. So if there's three variables, x, y, and z, remember we need to have three equations. So this first bit of information here is that there were 1,175 tickets sold on that day. And those tickets are comprised of each of the three different types, X, Y, and Z. So if there were 1,175 total tickets sold, then the first equation would be number of child tickets sold plus number of adult tickets sold plus number of premium tickets sold is 1,175. So there's our first equation. Okay. The next bit of information here I chose was the cost of each different type. So the $7 for the child, $10 for the adult, and the premium seats were $12 a piece. And the total that was brought in for that day was $10,950. So the equation there could be $7 multiplied by the number of child tickets. That's the amount of money brought in by just child tickets. If we add that to $10 multiplied by the number of adult tickets, that's 10y. So this is the amount of money raised by child tickets plus the amount raised by adult tickets, and then we add the amount raised by premium tickets, which is $12 times the number of premium tickets sold. So this could be our third equation, 7x plus 10y plus 12z. This is the amount of money for each ticket, totaling $10,950. Now the next statement here is a little tricky. Twice as many adult tickets as child tickets were sold. Twice as many adult tickets as child tickets. So the statement there deals with adult tickets Y and child tickets X. So this statement here is going to include X and Y. Now twice as many adult tickets were sold as child tickets, so they're not equal. So when I'm starting to make an equation here, X and Y are not equal to each other because it says twice as many adult tickets as child tickets were sold. So already the adult tickets is twice as big as the child tickets. So if I wanted these two to equal each other, I'm going to have to multiply this by 2 so that it equals the amount of adult tickets. So the statement there is that 2x equals y. So now if I take the child tickets number sold, multiply it by 2, that's going to equal the number of adult tickets sold. So 2x is equal to y. That's where this third equation came from. I just subtracted y to get it equal to 0. So we've got our 3 equations set up. So the only thing left is to solve. So the bottom equation already has z missing. We only have x and y. So what I chose to do is take these top 2 equations, and I wanted to eliminate z since this equation already had z missing. So if I multiply this top equation by negative 12, which I did here, and then add it to this middle equation, z eliminates, leaving negative 5y minus 2. That should be negative 5x. There we go, minus 2y. So then I combine this negative 5x minus 2y equals negative 350 with the equation here, 2x minus y, which already had z missing, and then you solve this smaller system of equations. I multiply the top equation by negative 2 to eliminate y. And then you can see here that x was equal to 350. Now it says there was twice as many adult tickets, so that means there were 700 adult tickets sold. And then if you add 700 plus 350, that's 10,050. The total was 1175, so I just subtracted to get z equals 125.